How's everybody doing? I hope everybody is enjoying themselves on this beautiful, beautiful day. Thank you so much for joining us. If you are tuning in, I am here today with Dr. Patrick Hossay in the Stockton Sustainability Lab, and we just accidentally started posting to the wrong account, so we're going to have to repeat everything that we just said, so excuse us if it sounds a little rehearsed. But this Stockton lab right here is the sustainability room where we have all sorts of fun toys that are actually the best of the best in the field, where if you are a Stockton major or a Stockton minor, they do offer a minor, you have the opportunity to work hands-on with the best equipment in the field so that you are appropriately trained when you get out of college to work in the industry, to make some real money in the industry, and to make some lasting change. We have a hybrid engine, a cutaway hybrid engine that you can play around with. We have solar panels. We have a fully functional windmill outside where you can look at wind energy. We are really close to Stockton's Atlantic City campus, where they are thinking about putting even more offshore windmills. We are in a really great place to study sustainable energy as well as sustainable agricultural initiatives. We have a sustainable organic farm on campus that we'll be visiting in 2 weeks. This is just really a fantastic major if you are interested in sustainability, and I'll let Dr. Patrick Hossay talk a little bit more about that and then introduce what we're going to be talking about for today. And I see we have 5 people on so far. Please feel free to ask any questions that you have about sustainability at Stockton, about the topic at hand. Please feel free to do it. I'll be here to answer any questions.
Awesome. So sustainability essentially is a major on solving problems we don't have answers for yet, right? How do we continue to make things, how do we continue to provide transportation, live our lives in a way that won't destroy the planet and that treats everybody fairly? That's sustainability. Since we don't have answers, we got to play around and figure out what those answers are. So this lab, Aaron's absolutely right, is about kind of play. It's about figuring out what possibilities are out there. So whether we're talking about alternative energy, new ways of designing cars, new building materials, or whatever it is, it's about kind of trying out ideas and figuring out which ones work and which ones give us better options. And today, I want to talk about geothermal systems. The geothermal system, strictly speaking, engineers call ground-sourced heat pumps. And I'll explain why we call them that in a minute. But a geothermal system is a system that takes the Earth's temperature and uses that for heating and cooling of buildings. And that's a fantastic way to heat and cool buildings because it allows you to be really super efficient. And that's what sustainability is about. It's about finding the best way of doing something. It's about creating buildings that we like to call high-performance buildings. Not just green buildings, but think of like a high-performance car. Like a building that can provide all your heating, all your cooling, be really well-lighted, be a really cool, livable space that you look forward to working in or look forward to living in, and also produces all its own energy or has no impact on the planet. That's the kind of buildings that we design. And one of the features we use is geothermals. Today I want to talk about geothermal systems or ground-source heat pumps. And I want to start with this unit, which is a small heat pump, to describe exactly what a heat pump is. And then after that, we're going to go outside and talk about the major heat pump we have here on campus, because Stockton University has one of the largest geothermal systems in the nation. It's really, and when it was built, it was actually the largest one in the United States. And it's really a phenomenal feat of engineering. So I want to talk about that because it's a really efficient system and it's a really cool kind of design. I think you're going to like it. But the first step is understanding how heat pumps work. So this is a heat pump. This is a small one. This wouldn't even heat a house. This would heat like a small cabin or something. It's scaled as a 1-ton heat pump. When we talk about heat pumps and we talk about heating and cooling, one of the units we use is a ton. And you know what a ton is. A ton is 2,000 pounds. But in heating and cooling, we use a ton as a measure of the ability of the unit to provide heating and cooling. And the reason why is kind of cool. The reason dates back over 100 years. Because if this were like 1890 and you needed to, say, cool a freezer for all your meats because you're a butcher, you would think about that cooling in tons because you would order a ton of ice. And it turns out that a ton of heating capacity is the energy, the heat energy released when a ton of ice turns to a ton of water. So if you were a butcher, you might say, okay, I need an order for 5 tons of ice, because that's enough to keep all my meat nice and cold. And so we still use the word ton and the unit ton to describe heating and cooling capacity. This is a 1-ton unit. A typical house in New Jersey would need about 3 to 5 tons for its total heating and cooling ability. But the more important question, getting to the point, is what exactly is a heat pump? Well, you know what a heater is. A heater usually burns something, natural gas or propane, to create heat. Or maybe it uses electricity. So coal is burned somewhere else, makes electricity, and the electricity produces heat. Heat pumps work a little differently. To describe heat pumps, I want you to imagine me as Superman, which is not a very large stretch of the imagination. I'm Superman. I take a little bit of air here. I squeeze the air tight. When I squeeze air tight, it gets hot. That's called the heat of compression. So I squeeze air and it gets hot. Well, you're cold. So I come over here, I release the hot air. Take more air, squeeze it over here, it gets hot. Bring it over here, release the hot air. And you're getting warmer because I'm releasing hot air toward you. Now I've made you too hot. Okay, fine. I'm going to do something different. I'm going to squeeze the air over here as Superman. Remember, I'm Superman, so I can squeeze this really tight, right? Squeeze it really tight. It's hot, but I'm going to let it cool off over here. So I move my hands about, it cools off a little. Now it's normal temperature. Now when I release it, what happens is I've got compressed air that I release. And when I release compressed air, it cools down. If you've ever sprayed a can, like a spray can of paint or something like that, and you felt it get cold, or maybe you had a propane bottle connected to a barbecue, and you noticed the propane bottle was getting some ice on it, that's the same thing. When you release the pressure, things cool down. When you increase the pressure by squeezing them, things get hotter. That's described by something, by a rule in physics called the ideal gas law. And we're not going to go through that too much, except to remember, you squeeze, it gets hot. You release something that's already compressed, it gets colder. That's what this does. It could do it both ways. If it runs in one direction, it squeezes and gets hot. If it runs in the opposite direction, it gets cold. So one of the nice things about heat pumps like this is you only need one unit to provide all your heating and cooling in your house. You can have this one unit, you run it in one direction, it heats the house. You run it in the other direction, it cools the house. A normal house would have like a natural gas heater and then an air conditioner.
So when we talk about a compressor in a system, that's you being Superman, right? That's the compressor.
Exactly. And another, besides me being Superman, you all are familiar with heat pumps because every refrigerator is a heat pump. That's what's going on in the back of your refrigerator. It's squeezing. When we talk about, I don't know if you ever noticed, your refrigerator is usually kind of quiet, and then every now and then it kicks in, it goes da 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 da. That's the compressor.
That's the Superman.
Yeah, that's the Superman. That's me squeezing, right? So normally inside the refrigerator, it's plenty cold enough, all the food is cool, and then it starts warming up, and the compressor notices that. It kicks in, it compresses a bunch of fluid, gets it all hot, runs it through the back of the refrigerator so that that fluid gets to be normal room temperature, and then it releases it through something we call a releasing valve or an expansion valve, and as it expands, like the spray can, it cools down, and it expands inside the refrigerator, so it cools down the inside of the refrigerator. That's basically a heat pump.
So magic.
Yeah. That is Superman, which you will now remember me always as Superman, which is important. And that is a refrigerator as well. So a refrigerator, actually, if you think about it this way, it's creating cold inside the refrigerator, but it's actually also creating hot outside the refrigerator. At the back of the refrigerator, there's something we call coils. It's a run of pipes. And those are taking that squeezed fluid and letting it run through to get to normal temperature before it expands it so that it can create a cooling effect. So the thing about that, the thing that's really interesting, is your refrigerator is kind of not really creating cold. And a heat pump isn't really creating heat. It's separating out heat and cold. And that's why it can be much more efficient. So the next thing I want to describe to you is imagine this.
That's also, FYI, why you can't just open your refrigerator and cool down your house.
Exactly. There's a Simpsons episode where like they set up a tent in front of the refrigerator and they're like there, enjoying the refrigerator. It's all nice and cool with like air conditioning, right? You're going to be shocked to learn this, but not all Simpsons episodes are absolutely scientifically correct. In that case, they were actually heating the house when they were cooling it, because when they left the door open like that, that compressor and coil in the back are working like crazy to keep the air conditioning.
Right, so you would just be
cold.
standing, because it separated the two, you'd be, if you were standing behind the refrigerator, you would be sweating your butt off.
Exactly, and it's actually creating more heat than cold.
Right, because it's slightly inefficient.
Exactly.
Right.
So, yeah.
All right, so.
So anyway, so here's the thing. Here's why it can be super efficient. I want you to imagine it this way. Imagine I have a bucket right here, right? And I take super hot water.
There's no bucket.
There's no bucket.
I'm bad at
I
imagining.
can imagine. And I pour in some super hot water. And then I take cold water and I pour in cold water. Now the test for Aaron to see if he's a true scientist. Aaron, approximately what temperature is the water?
I was ignoring you for a second. Say that again. Okay. Wait, I'm going to be a student. What was the question?
We're going to withdraw Aaron's credentials.
Yeah.
The water's now, whatever, mild temperature, lukewarm, right? Room temperature. Because I put in super hot, super cold. Now it's normal temperature. Okay, you understand that. That's pretty easy to understand. Heat pump allows us to do the opposite. Imagine I have lukewarm water, and I could separate it out into really hot and really cold water. That's what heat pump lets us do. And because of that, we aren't actually generating heat, we're separating out heat. So while a normal heater, the maximum efficiency it could have would be like, 100%, or not even, it's never going to be ideal, so let's say 98% efficient. A heat pump can be many times effectively more efficient because it doesn't generate heat. It separates out the heat. So actually, when we talk about heat pumps, we're often talking about coefficients of performance of 3, 3.5, or 4. Essentially, 400% efficiency. So when you compare it to, say, a propane furnace, it's 4 times more efficient than a propane furnace. So already, that's awesome for the environment because we're not burning coal or other kinds of things to generate electricity, heat and cool our houses. We're much more efficient. But to really understand how heat pumps can be awesome, we need to go outside and take a look at the Stockton system. So let's go do that.
All right, guys. So I'm going to...
This is the lab. It's an amazing place. If you want to major in sustainability or even come by and visit, you're welcome to.
Plus, you have 1,600 acres of pine barrens forest and a fully functional organic farm.
There is no better place to study this
From what I
stuff,
heard, this guy that we're talking to right now, for a final project in one of his advanced classes, he just rips the wiring out of a solar panel and then makes you reconfigure it.
If only that were a final project. That's a normal project, I think week 3.
Oh. See, you're really going to have to learn like what you do.
So you can see that we've got all kinds of stuff here. And of
Look at
course,
the toys.
The cool thing is, what I don't do, really, is have the students kind of just work on this by saying, you got to measure this, you got to measure that, you got to do this and that and the other thing, because all that is boring as heck. What I do is I tell students, here's an interesting wind turbine, figure out how it works. Or like Aaron said, here's a solar system, I've torn out all the wiring, fix it. Because that's how you really learn, problem solving.
I know how to fix it.
Sustainability
You call an
majors
electrician.
are about solving problems and finding answers. That's our real major. All right.
I'm just going to call an electrician.
This looks like a normal parking lot, but looks can be deceiving. Because this parking lot is actually one of the most amazing things on Stockton's campus.
So for reference, everybody, where we are on Stockton's campus, just so you know, this is, let me turn around here, this is the new Health Sciences building. For those of you that have ever driven down Vera King Ferris, you can see the sign in the distance. That's where everybody likes to take their graduation photos. So this is lot 1 over here. You can see the spine down there. This would normally be filled with cars and impossible to find parking. And now we're going to find out that looks can be extremely deceiving.
Exactly. And after I talk about the parking lot, we're going to go over there to what's called the Manifold House. This is kind of cool because you're going to be an insider on this. The Manifold House, everybody passes it. People park here. They walk by it every day. Nobody has any idea what it does.
Yeah, seriously, I worked here for 2 years and I had no idea what it was.
Okay, this parking lot here looks like a normal parking lot. It is not. Back in the late 90s, in order to allow heat pumps to work even more efficiently, we tore off this entire parking lot, took 4 feet off the entire parking lot, and we drilled 400 wells. So under this parking lot are 400 wells about 15 feet apart from each other. Literally every 15 feet, there's a drill hole that goes down 425 feet. 400 wells, 425 feet, every 15 feet. A huge grid. And we connected all those together with pipes. All together, 60 24 miles of piping under this whole parking lot. Looks like a normal parking lot. It is not a normal parking lot.
We're talking about vertical as well as horizontal.
Yeah, so they
distance.
Yeah, exactly. So they drill down 425 feet,
Yeah.
drill back up, and then go to the next one, drill
Okay.
down, go back up, etc. And the manifold house is about taking all those different pipes and connecting them together. That's what
So guys, if you need some help imagining this, imagine the back of your refrigerator. Imagine all of those pipes going up and down and up and down and all connected to each other.
Sure.
That's what's underneath of this asphalt parking lot.
Exactly. And the point of that is this. We talked about heat pumps a second ago, right? Okay, so far you got that. But imagine this part of it. What if in the winter, instead of taking 10-degree air and having it to warm up to like 80 degrees in order to warm my house, what if I didn't have to take 10-degree air? What if I could start with, say, 59-degree air? What if in the summer, instead of taking 100-degree air and cooling it down in order to cool my house, I could start with 59 degrees? That's what we do here. The ground temperature is about 59 degrees. So instead of taking outside air that's really cold in the winter, really hot in the summer, and bumping that up or down for heating and cooling, we can take a consistent and steady 59 degrees from the ground and feed that into our heat pump. So now when I'm Superman in the winter trying to keep you warm, I don't have to start with 5-degree air to squeeze. I can start with 59-degree air, which makes it a lot easier for me to squeeze, so I use less energy. So it actually increases the efficiency of the unit dramatically. So that's why engineers don't call this geothermal, we call it a ground-sourced heat pump, because it's a heat pump that's using as its source the ground temperature. Let's go take a look at that building over there. Did you see that building way over there? That's called the manifold house. And a manifold is something that takes a bunch of pipes or hoses and connects them all together. That's what that building does. It takes all the wells we got here, 400 of them, and connects them all together into a single manifold, so that can be used to feed heat pumps. The heat pumps themselves, I can't really show you because they're all on top of buildings. So our main spine, the campus center, and the Arts and Science building all have heat pumps on them.
But the thing that you were standing next to inside of the building was essentially a mini-scale one.
Yeah, so that's a small one. Most heat pumps here are
Much
5
bigger.
to 25 tons, so they're significantly larger than the little one. That little one's one that our students
5 to 25 tons, not in weight, but in capacity, you mean?
No, but they might be a couple of tons in weight.
Okay, yeah, right. So remember, in terms of capacity, when we talked about those gigantic ice cubes, you know, how many tons of ice cubes would it need to cool down your house? That's what he means by 5 to 25 tons
Exactly, yeah, right,
capacity.
exactly.
So, Patrick, what happens if we ever need to do maintenance on all of those wells? Are we in for just throwing away the system?
That's a really good question. In fact, it actually brings up also something that's really interesting. If we built one of these now, we'd have running through that pipe a special fluid, something like propylene glycol that is really good at collecting heat, holding on to the heat, and then distributing the heat. But when we did this, we were one of the first to do something like this, so we actually just filled it with water. Now you wouldn't do that because water is not quite as good at transferring heat. But we thought exactly this. What if we get a leak? What if this doesn't work out the way we expect? So we decided to use water, so if there is a leak, there wouldn't be any damage.
Right, and we're on top of the Hossay Aquifer, and we definitely don't want that.
Exactly. Propylene glycol is food grade. You shouldn't go around, well, you've probably eaten some today. I was about to say you shouldn't go around eating it, but if you've had it, a lot of produce foods have propylene glycol in it. It's the thing that makes beef jerky kind of slick. Have you ever wondered how like a chewy cookie is chewy like 2 months after they made it?
I don't eat slick beef jerky.
That's propylene glycol, which is actually an industrial coolant.
That's not comforting.
Anyways, that's what we would normally use in this system, but that's not what we use. In addition to that, we have got about 15 wells here that we can use to evaluate the system. That are additional wells where we can drop down sensors and see if there's any leaking.
And as part of your classes, I understand that you actually have students do take samples from those wells.
We kind of used to, and I think some faculty are still doing that, but honestly, it got kind of boring. I mean, the system's been in place 30 years. We've got no leaks, no issues. Everything's operating great. There's only so many times you can check like a great system to find a problem and not find a problem before you're bored with it.
Well, I'll break something if you want.
So that is one answer to this, is we monitor it closely, it's filled with water, so if we get a leak, it's really not going to be a big deal. In addition to that, I got to show you inside the manifold house.
And what's the lifetime on all of the pipes?
Oh my gosh, they're PVC,
like
so I don't know,
hundreds.
1,000 years?
Cool, cool, cool. I seriously had no idea what this building was for the longest period of time.
This. Here's the lights.
It's spooky.
Here we go. Manifold house.
Nice.
This is the manifold. So these long tubes connect with these. Each one of these has 20 wells. Is it 20? I can't remember. Has a bunch of wells that connect to it. So all those wells out in the parking lot connect to these, which connects to this. This then has pumps over here. Come on in. If you look in this room here, it's just filled with industrial scale pumps.
It's a little loud.
Awesome, right?
Sure,
Somebody should
scary.
in so they can see like lizards and creeks and things like that, and then they get this. So all that fluid comes into here and then gets redirected. First off, in terms of safety, the question Aaron had, if we had a leak, I could just turn this off. So we can isolate certain parts of the well to make sure that we don't get any undesirable leaking. Then when it's all collected together, it goes to the top of the buildings where it's used to feed the heat pumps. So again, the heat pumps start at about 59 degrees. I could actually tell you what the ground temperature is now. Yeah, about 60 degrees. So it's warming a little, which isn't shocking actually. One of the problems we have with this system is that it's warming up a little bit, and we'll go outside and I'll explain what that is. But these are the manifolds, all connected to pumps, go into the building, feed the heat pumps.
So inside of this black pipe is really just a bunch of groundwater.
Not groundwater. It's a closed system.
Oh, that's right. It's a closed system. So it's a bunch of water that's in a closed system that's being cooled by the ground, and then flowing straight down in there. And then where?
It goes up here, up there, across that pipe, and into the main campus. In fact, you can see right here, back up here, Aaron, you'll see. There it's marked, Geo Water Return. This is the water that's coming back from the Geo system.
Oh, okay. Okay. And then what this other pipe is doing the same exact thing.
Yeah,
it's just for the other sets of wells. All right. All right. So this system actually is, in principle, very, very simple.
Yeah.
I mean, we're not talking about, but actually getting it to run correctly.
Let's step outside maybe so that people can hear us.
Sure.
Oh, I do have this here. I don't know. Can you get a shot of this?
Yeah.
There is the parking lot back when we initially put that in place. You can see it's all torn up. And there's the pipes that we put into the ground.
Wow.
Cool, right?
What a massive undertaking.
I know. Can you believe we did that?
Expensive at the time, but it's saved the university so much money.
Oh yeah, it's paid for.
And of course saved so much electricity.
Yeah, we approximate that this reduced our natural gas use by 70%, and it reduced our and that's normal, right? Because we're not using natural gas now; we're using electricity through a heat pump. But it also reduced our overall overall electrical use by about 20%. So a 20% reduction, even though you moved all your heating and cooling to electrical, and a 70% reduction in natural gas, it's probably reduced our overall carbon footprint. We did an assessment of this about 10 years ago. I would guess by about 14%.
So, and what on campus is it cooling? Is it cooling all of the buildings?
It's
or?
cooling most of the main spine from the campus center over to the right. It's cooling the campus center, and it's cooling the Arts and Science building.
So for those of you that aren't familiar with our campus, because I'm not sure where everybody's tuning into, and by the way, if people are asking questions or making comments, for some reason I'm not able to see them, I have to figure that out later on, and we will be more than happy to answer them after the video is done, and we'll post them. We will just ask your questions away, and we will answer anything that we see later on. So if you're not familiar with our campus, the spine is the bulk of campus. I mean, we're talking a huge footprint. Unlike most campuses, Stockton University is actually fairly simple because it's just a one long building. At least the main campus is one long building.
Think of an airport.
Yeah, it's essentially just an airport terminal strip of classrooms and offices. And so if you work on campus, chances are every single day, no matter where you live, where you work or teach, at some point you are being cooled or heated by this system.
Right. And here's the interesting thing in terms of size, to wrap your head around the size. Remember that heat pump I showed you before, 1 ton? typical house, 3 to 5 tons. This system's capacity, operating capacity right now, is well over 1,500 tons. So roughly the heating and cooling necessary for about 400 to 500 houses being used by this system. And it's just one, it's the biggest system, but it's just one of the systems on campus. We also have completely separate systems in our facilities building, at our daycare center, several other places. So we have well over 2,000 tons of heating and cooling geothermal capacity on campus. That is huge.
Now you mentioned that Stockton was one of the first to do this. As of now, how many places around the world are maintaining such a system?
This scale?
At this scale?
Hundreds.
Hundreds.
Yeah, I mean, it's been 30 years since we did this. I mean, at that point, there were dozens in Europe and several others in Asia, in Japan in particular. We were the ones that sort of took this on in the United States. And even now, our model, we don't as much anymore, but we used to get visitors from all over the world. In the late 90s and early 2000s, we had conferences here. People would come to see this system because they wanted to mimic it.
Yeah. And this kind of system really can be scaled down or scaled up. I mean, this is pretty large.
Well, you can have this in your house. It's
right,
not common to have, again, a 3-ton system in your house. My own house, actually, because it's very, very efficient, it's a very, tight system, has a 2-ton unit. That's what I need for my house, which is really small for a house, but it's a very efficient house. But still, a normal house would have a unit, and you have, in my case, one single well, a 200-foot well, under the driveway.
So, just to recap, everybody, what we've been talking about today, and thank you for those of you who are joining. By the way, we've had about 10 to 15 people on average on the stream, so it's been good. And this video will be posted online afterwards, and so for everybody that wants to view it, so this is good. What we've been talking about is our aquifer cooling system, our groundwater exchange.
Well, we're going to get to
We're going to get to that. So our groundwater cooling and heating system.
Love it! It's not groundwater.
It's not groundwater. It's, what do we want to call it?
You can call it a ground source heat pump or
ground
geothermal.
Source heat pump, geothermal. We'll call it geothermal. We've been talking about our geothermal pump. We're going to talk about our aquifer thermal exchange system in a second. But so what you can see behind me is the asphalt parking lot where we have all of the wells that contain a closed system, closed loop water circulating system that is pulling heat and heat out of the ground during the winter. Is pulling essentially pulling heat energy out of the ground during the winter. Is essentially pulling placing heat energy back in the ground during the summer, and through some sophisticated pumps in there, pumping all of that energy into the main campus. Now, it's a little bit more complicated than that. You can rewatch the entire thing if you need a better explanation.
I actually like the way you said it, because you said, essentially, we're taking heat out in the winter, and we're putting heat back in the summer.
Right.
That's a really good way of thinking about it. So here's the problem.
That's what I wanted to get at. I wanted to lead into the problem so that it was continuity.
In a climate, that might be beautiful, right? But not all climates have an exactly an even balance of heating and cooling. So imagine if you're in, like, I don't know, northern Alaska, you need more heating than you need cooling.
Because it's cold.
Because it's cold. So if you're in Florida, you need more cooling than you do heating. So in our case, if it were balanced, then everything would be fine. We'd take out a certain amount of heat in the winter, we'd put back a certain amount of heat in the summer, and it'd be balanced. But we're not exactly balanced. We have a bigger cooling load than heating load here in New Jersey.
Because it's kind of warm.
So we're actually putting more heat back in, which means the first 10 years or so that we use this system, the ground under the parking lot was starting to heat up. Now that wouldn't happen in a small system. So if you have one of these in your house or in my house, you're never going to heat up the earth.
Right.
With your little geothermal system in your house. But here, there's enough wells, again, 400 of these, each 425 feet deep. There's enough wells where you get localized heating. The heat can't dissipate effectively, so it starts to get warmer. And as it gets warmer, it becomes harder to put more heat in. So we get inefficiency. So actually, we had a problem for the first 10 years of this, which was that imbalance that was causing local heating in the ground here in what we call a field. This is called a geothermal field. And so we solved that in a brilliant way. And I want to show you that by walking you over here. So come on. And as I walk, I'm going to point out that the sustainability program, again, is a hands-on kind of stuff, just like the environmental science program and the excellent marine science program here. This is our hybrid.
Wait, why are we excellent?
Vehicle.
Why do they get the excellent adjective and we don't?
This is our electric vehicle. This actually belongs to Stockton's sustainability program, so our students can experiment with electric cars.
Wait, we own a hybrid vehicle?
Electric.
We own an
All electric.
So I don't pay attention to people. We own an electric vehicle.
Yeah.
That's pretty neat.
If
Okay.
you came here as a student, you could take a class on sustainable vehicles where you would test that thing and play with it, and these charging stations.
Free of charge?
Yeah. These are actually owned by Stockton. This isn't a vendor. So plug in, you get free of charge.
See, we don't have a Tesla.
And if you come out here on a typical day, they're full. I thought actually when we first got them that it'd take time before they filled up. Turns out, no, there were people dying to have charging stations. So on any given day, those are full. So I want you to walk over to this. And what I'm walking you over to is something called an Aquifer Thermal Energy Storage System, which is a mouthful, so we call it ATES.
So just to remind you guys, the problem that we're dealing with, all right, so we have this geothermal, essentially a geothermal unit where we're cooling or heating up campus. The problem is that we have an unbalanced hot and warm seasonal cycle here. And so we're going to wind up heating the ground up a little bit more than we're cooling it down. And so over the time, we're going to wind up overheating the ground, and it's going to drive the system into extinction unless we do something about it. And so the solution to that is one of the coolest parts of this system. Environmental science standpoint, I think that this is just neat.
Yeah, this is awesome.
Something that most people on campus just completely ignore. They don't even know what it is. They just bypass it. Right. I mean, this looks...
That's something where you're going to stop and go, oh my God, that's beautiful.
No, it just looks like it's plumbing, right?
That's right.
So what is this?
Plumbing is, by the way, visible like that. We could have just put that in the ground or in a building or something like that. We put it under this plastic cover because we wanted people to see it so that I could take you and other students out here and we could talk about it. In fact, just as kind of a little inside baseball note, this plastic cover we had to search around for. You know what it is? It's actually a bike storage locker from the Netherlands. So the other side flips up, and you can imagine if you had one of those on your street, you could flip it up, slip your bike in there, flip it back down, your bike's safe and dry overnight, etc. So that's actually what this is meant to be, but we use it to cover a wellhead. We have 3 wellheads on this side of campus, and then 3 wellheads about 1,000 feet away on the other side of campus. For those of you that are familiar with Stockton, they're over near the West Quad. And here's what it does. This is really cool. Remember, we have more cooling load than we have heating load. As a result of that, our geothermal field is getting warmer. So how do we do
the geothermal field, meaning this asphalt parking lot. It's not a field, it's a parking lot.
What's under it, actually? The parking lot itself, we don't care about it.
Right, the parking lot is going to be hot no matter what, but we're talking about the ground, the soil underneath of the parking lot.
Right, going down several hundred feet. So to solve that, we thought, wouldn't it be interesting if we could take some cold from the winter and kind of store it?
I do that all the time. I take a snowball from the winter and I put it in my freezer so I can throw it at somebody.
You know what? That is something that actually was done in history. That's how you got ice. So 150 years ago, if people wanted ice for, let's say, ice cream in the summer, they had to be aware of that in the winter. So in the winter, when the lake froze, they'd go out there, cut a bunch of blocks of ice, put them in storage, and keep them for months so they could have cooling in the summer.
Yeah, just a quick shout out. There's a really great podcast on that related to alcohol and the tipsy timeline because there's a whole reason why you currently drink all of your drinks cold. 100 years ago, you didn't do that because they didn't have ice makers. So there was like, what was his name? The King Man or something? Iceman? Ice King. What was his name? I can't remember. This is a guy that made a profit in just shipping ice all around the world.
Yeah.
Anyways, okay.
Yeah, right. From like Rochester, New York or something.
Yeah. Okay. Anyways, so we're not storing ice cubes in freezers here. What we're gonna do?
That's an awesome idea, right? Like storing winter to use in the summer. Brilliant. But how do you do that? We do it in the aquifer. You've probably watched Aaron on some of these podcasts, so you know this. But essentially, the aquifer is like an underground storage of water.
They don't know that.
They don't know that?
No, they don't know that.
So if I dig down anywhere on the planet, at some point, well, maybe not anywhere on the planet, most places on the planet, some point I'll hit water. Maybe it'll take me 50 feet, maybe it'll take me 200 feet, but the ground starts getting wet. And we sometimes call these underground streams. They're not really underground streams because it's not like a big cavern filled with water, but it's just saturated soil. So it's in the ground, water moving through the ground. Well, it turns out one of the bigger ones is right here. And one nice thing about it, it's not really a river here. It's more like a lake. It stands pretty still.
Right here?
Exactly.
What do you mean right here?
So you could drill down right there, you would hit water. And you know this if you have maybe a house that's on a well, because you have a well that's drilling down and picks up water and sucks it out of the ground so you can take a shower and drink water and things like that. Okay, so there's water in the ground. So far, so good. Here, the water doesn't move much. Some places it moves a lot. Here, it doesn't move very much. So here's what we do.
If it did move a lot, we actually wouldn't necessarily have this problem, right? If it did move a lot, the water would be exchanged. But because it doesn't move a lot is why we actually have this problem.
I'm not sure that's entirely true, but the logic is right. That is, if the water moved more, it might create cooling for the geothermal field. I'm not sure it produced enough cooling, but who knows, it could. So what we do instead is this. We drill down into the aquifer, which isn't much, 100 feet. I think these aren't even 100 foot. I think they're like 85-foot wells. I can't remember. We drill down into the aquifer. We suck the water up. Lots of water. You see how big that is? A normal wellhead is like this. This one's huge. We suck up a lot of water. We bring it over there to that manifold house, and can you see from here to the left side of the manifold house, that big silver thing? Are you touching it?
Yeah, I'm trying to touch it.
Awesome.
I'm trying to touch it. It's
that
like this part
is
right
like
here.
a big radiator or a heat exchanger. So we suck the water up, we put it through that heat exchanger, and then we put it back in the ground. And we do that in the middle of the winter. And what that does is it cools the water. We're essentially taking groundwater, lots of groundwater, massive amounts of groundwater, cooling it down when it's like 5 or 10 degrees out, and then putting it back in the aquifer. So the aquifer gets colder. That's why we call it aquifer thermal energy storage.
Now you do this during the winter because that's when it's most efficient to do it.
Well, no, that's because that's when it's cold enough to do it.
Right.
If you did it in the summer, you'd warm up the aquifer.
Right, okay. Well, I mean, but the radiators are cooling it down as well. They're exchanging air.
No, they are just using ambient.
Oh, they're just using ambient. Okay,
Yeah,
so
yeah,
there's no
Yeah,
cooling.
yeah.
Okay.
Yeah. So it is just essentially exposing aquifer to really low temperatures. So it is set to work when it's cold in winter.
So what we're doing is then we're sucking water out of the ground and then cooling it down above ground, and then we're going to shove it back in the ground, storing it like we're storing an ice cube in the freezer over the winter.
And now you can see why it's important that the water doesn't move much. If our water flowed through, if we're like an underground river, we'd suck a bunch of water up, cool it, suck it back, or blow it back down, and it'd be gone a month later. We've got to be able to do this in January and December, and then pull it up in July, which means it can't move much. And it turns out here, because there's not much movement, we're able to get back over 90% of the cold that we put in the ground. So we suck up water, we cool it down, we put it back in the ground, and 6 months later, 90% of that cold that we've stored, that winter cold that we've stored in the ground, is still available to us. And then we use that to pre-cool the air. So imagine another radiator on the roof where we have those heat pumps to pre-cool the air before it goes into the geothermal system. So now, not only do we have a geothermal system which provides, stable, roughly 60 degree temperature, but we can pre-cool so that in the summers, when we need the air conditioners, we can lighten the load on the geothermal system by dropping the temperature of the incoming air 7, 8, maybe 12 degrees before it comes into the air conditioners. And that makes air conditioning a lot easier, and it makes it much more efficient. All this combined means that we've got the most efficient university in New Jersey for heating and cooling. If you compare the amount of money or the amount of energy we use for our heating and cooling per square foot of campus, we are way lower than any other campus in New Jersey. It's a brilliant system, right? It was kind of expensive to put in, but it's more than paid for itself because we save so much money in energy costs.
So, I mean, for reference, I know that there's a bunch of sustainability or people interested in sustainability. You can do this for much cheaper at your home. On a small scale. The reason why it was expensive here at Stockton is, of course, because we have an enormous amount. What did you say? We needed about 150 tons just for the spine?
Yeah, I mean, kind of think of this. We had to tear up the whole parking lot, put in all those wells. In addition to that, we had to get a helicopter, put all the units on the roof. So this was a major undertaking.
Well, you can fly a helicopter, right? This system that we're talking about right here is not a fully closed system like our geothermal. This system is actually pumping water, is actually exchanging water with the ground between a pipe and the ground, and it's then pumping it to an area where we're going to cool it down and then store it. Now, you mentioned that it's pumping it a far distance over. For those of people that are familiar with Stockton's campus, where is the aquifer that we're actually pulling this
Well, the
energy
aquifer
from?
is under us in the whole area. We've got 3 wells here. So right now we're outside of 8.
So the other well, in case you didn't know, that's that building right there, and then we have another one over there.
And then near West Quad, or in between West Quad and the campus center, there's 3 more wells. So those 3 wells are separated by about 1,000 feet. Actually, it's 975 feet.
So we've got a football field.
Yeah, and the reason for that is because you can't like pump down water at the same time that you're trying to suck up warmer water.
Right.
You have to be able to suck up warm water and then pump down cold water. So, excuse me, we need some separation. So that's the idea of separating them out that way. So 3 of these wells deliver, the other 3 wells suck up, and then when the season changes, they reverse roll.
So what are the downsides to this whole system? I mean, you definitely need to use electricity for some of these pumps, but of course the electricity is much less than you would be using in traditional heating and cooling systems. So what's the downside to this?
Well, one is upfront cost. I mean, it wasn't free. And the other is that it's got to be the right location. The thing about alternative energy, wind energy, solar energy, geothermal, all these energy sources, is they're not sort of just like one size fits all. They have to be designed for this particular use. So if you have a solar panel, it's got to be in a place where it's going to get sun. If you have a wind turbine, it's got to be where there's wind. And for this system, let's say the ATES system, we need to have a system where we had plenty of aquifer capacity and an aquifer that wasn't moving. Imagine the opposite. Imagine we had an aquifer that moved really quickly. Not only would it be really inefficient, it could actually even cause ecological damage because it would be cooling down the aquifer. At some point, it comes back up into the ground, from the ground as a spring into, let's say, a creek. And that creek, by the result of us cooling it, could be 5 or 6 degrees cooler, which may make it too cold for crawfish or whatever else. I'm making stuff up here. Aaron would know better exactly what species would be harmed by a 5-degree difference. But the point is, we'd make an ecological change that would be undesirable, and we wouldn't be able to harvest the energy return that we want.
Yeah.
So this fits because we've got an aquifer that has the capacity and that has the stillness, if you'd like, the residence time, to make it work. The same thing with the geothermal. We had a large parking lot. We had a large demand. It made sense to do it. Does it make sense in all situations? No, not necessarily. In a different situation, we might have made it differently.
So, correct me if I'm wrong, Patrick, but one of the things that's really that you really learn in sustainability is how to assess the needs and the requirements of a particular area to deliver sustainable technology to that area. I mean, really, sustainability is not about a one-glove-fits-all. If we're going to live sustainability, we have to be on smart grids, smart networks. We have to have a combination of different types of renewable energies like solar, geothermal, wind, and it's really up to the trained sustainability student and the subsequent worker to assess a site and figure out it'll work for this. I mean, it's the irresponsible sustainability student that goes to a site and says, oh yeah, let's do geothermal here, but then doesn't actually assess the environmental hazards associated with it, or more importantly from the energy standpoint, whether or not you're actually going to get any gain from it.
You know what, let me make 2 points because you're making a really interesting point. 2 things I'd want to say. One is I always tell my students, you are not an advocate for wind energy everywhere or solar energy everywhere, because that actually does the earth harm. Imagine that you're like really into wind energy, right? So some farmer says, I want a wind turbine. You don't even look at the site. You say, of course you want a wind turbine. They're awesome. Put in a wind turbine. Okay, then you put in a wind turbine and it stands perfectly still because it doesn't have enough wind. Well, what help have you done for the planet? People see that wind turbine and they're convinced wind energy doesn't work because that turbine's never spinning. And we spend a certain amount of energy and resources making a turbine that's doing no good at all. So we've actually harmed the planet. So you're absolutely right. It's got to be the right fit for the right location. The other point I wanted to make is when people come to me, students come to me, and they want to major in sustainability, what I tell them all is that sustainability is very complex. So they have to expect to be frustrated. They have to expect to be challenged. They have to expect to have to explore. And in the end, if I've done my job right, when they graduate, they will have fewer answers than they have now, but the answers they do have will be right. Because here's the thing. People come to sustainability with like an idea, like solar panels, that's the way to do it, or electric cars, that's the way to do it. But it's not always that. Sometimes electric cars make sense, sometimes they don't. Sometimes solar panels make sense, sometimes they don't. Things are complicated, even bigger than that. A carbon tax or a new policy on this or a new policy on that. Yeah, sometimes it makes sense, sometimes it doesn't. Sometimes it's to change to fit the situation. Sometimes it's going to be a good outcome, sometimes not a good outcome. So what I tell the students then is that when they graduate, they'll be thoroughly confused because it'll be so complicated. But they'll be confused in a good way because they will recognize the complexity and be able to work through it. So the answers they do get are much more likely to be correct because they won't just be made up. They'll be based on solid science, solid understanding of economics, of business, and politics. In fact, sustainability majors, kind of unlike environmental science majors, have to take core classes in environmental policy, in ecological economics, in ethics and other issues, as well as in the typical classes in ecology and other areas, so they can put all that together to come up with answers.
Yeah. So it is kind of the same way in any scientific field,
Yeah.
but particularly in fields like sustainability, marine science, and environmental science, where the information that we get now to improve our planet, it's just changing every single day. And so as educators, Dr. Hossay and myself, and anybody else here at Stockton who teaches these kinds of fields, the best thing that we can do for you is to confuse the crap out of you.
Exactly.
I mean, the best thing that we can do is really to teach you that we're not going to be right? I mean, we got to teach you how to think independently, how to think for yourself.
Even better than that, there's no right answer.
There is no right answer. I mean, if you guys just want to install solar panels, or if you just want to run plumbing, you can get your education for much cheaper, wind out on top. And I'm not saying anything against that. You can make a lot of money and do a lot of great things. But if you're interested in like getting new initiatives out there, doing really cool new sustainable things, and being the person in charge of everything, I mean, you really got to learn how to think independently. And that's what we're talking about. Like, we're not talking about teaching you how to run plumbing. That much you can go to a 2-year school and get your degree. And trust me, I'm not saying you shouldn't do that. Lots of people do that, and it's a lot of fun, and you make a lot of money. You can have a really great living. We're talking about doing the research and informing the public about the newest initiatives.
Yeah, and that newness, that's the cool thing, right? I get so many students that graduate, and they come to me and say exactly that. Like, it was awesome. Last week we worked on a project. Nobody's ever done this before. Nobody's tried that before. Nobody saw this as an option before. And I think you're absolutely right. Like, we know how to install solar panels. So you can go to a community college and get training in solar power installation, and that's awesome. And here we do train people. They get certified in solar power installation because they have to know that to take the next step. But the next step is, okay.
But those are your basic courses.
Yeah, those are your basic classes. The next step is, okay, but how do you apply that in a situation that nobody's ever applied it to before? Or how do you make it even better? How do we devise a mechanism where maybe the solar panels can actually follow the sun across the sky, as one of my students did in the last class? Or how do we devise a mechanism that will heat a house using just the sunlight that hits its windows? Or other kinds of things like that. So there's all kinds of ways that students play with new ideas and new possibilities, and that's what we need. That's the technology we need to kind of fix the bind that our planet is in.
Yeah. Yeah, I mean, like, yeah, don't get me wrong, it's a lot of fun. You have that cutaway hybrid to kind of learn all about that stuff. The first time I saw that, I was mesmerized by it. That is the
lab device that you fixated on.
I absolutely love that, because I mean, I'm kind of a gearhead. Like, I love I don't know a thing about cars, to be honest. I can take a wrench and take it apart, and I'm not sure I can put it back together. But the basic classes, you learn how to do this stuff, and you become an expert in doing this stuff at Stockton. And then on top of that, your advanced classes, you learn how to improve it. You learn how to think for yourself. So let's just zoom in on this thing again. So, by the way, for those of you that have tuned in, I'm sorry if I haven't been able to address any questions or comments. I don't know why I can't see them. I'll have to fix that on the next stream. But so this is our Aquifer thermal exchange system, ATES. There's another word in there.
Energy.
There we go. So what we're doing is literally cooling down an entire aquifer or an underground lake in the soil. and using that energy using that system to cool our buildings in the summertime. And that is working in conjunction with our geothermal system, which is this building right here, which if you ever drive on Stockton's campus, you might miss it. You might be parking right underneath of it. I've seen people parking just underneath of those gigantic I've seen people parking just underneath of it. That thing is responsible for cooling a huge chunk of our building. We have another system, a smaller system like this on the other side of campus, yes?
Geothermal, we've got about 5 of them around.
Yeah, so we've got about 5 of them around campus. We're really trying to improve sustainability. So we've been chatting with, and just ask your questions and we'll get to them after this is over. I promise you we will do our best to answer all of them. So for reference, for those of you that are tuning in, we are walking on lot 1 right now. There's the campus center. For those of you that are coming to campus this coming semester, you'll probably be parking here. You can lounge about in there, but hopefully when you do lounge about in there, you recognize, although I don't know if that building is not cooled by the, oh, it is. The campus center is. So you'll be cooled or you'll be heated up if you've tuned into this live stream. Sit there and appreciate it.
Also, Bob, like we're there a lot. Well, I don't know how to just kind of poke your head in, see what we're up to.
Yeah. Dr. Hossay, he just basically knows everything. So
I think I've been insulted in a very kind way.
Don't be intimidated. I'm pretty sure that he could take your entire car apart and put it back together.
But that's not hard.
And then I'm pretty sure that he didn't you parachute? Weren't you a parachuter?
I 7 years in the Navy, yeah.
Jesus. Yeah, no. Dr. Hossay is so skilled and talented that he makes my life feel like a joke sometimes. Yeah. Anyways, by the way, I'm sure that, I don't know if anybody's asked this question, but I'm sure that maybe somebody was thinking about it with this aquifer. And, you know, as an ecologist, as somebody who focuses on the planet, that's a given. We are going to change the planet. Sustainability is the field that works saying, okay, well, if we are going to change the planet, how can we change the planet the least? Or for the better, so that we can continue to sustainably interact with nature. And honestly, I really can't see, as long as it's done responsibly, as long as it's sited properly so that it doesn't heat or cool down a nearby lake, it really isn't doing much damage. This is truly one of those things where we are responsibly using the Earth's resources.
There's a certain amount of energy that was used to make the system. You could say that had some damage to it, but we've way overcompensated for that in the energy we've saved.
Right. And I mean, no matter what, we are going to affect the planet somehow. There's no way that we can exist. There's no way that any species can exist without affecting the planet and consuming resources. We just have to make sure that we do it in a responsible and sustainable way. All right, guys. And with that, thank you very much for tuning in. Tune in next week with... We're here. We're going to go to the and we're going to explore the greatest greenhouse in Galloway, which is probably one of the only greenhouses in Galloway. It's kind of a small town. Anyways, so thanks for tuning in. I'll catch you later.